Hello, everybody. Welcome back. So today we are talking about Lewis acid-base chemistry. This lecture is going to be a little shorter, considering the last one was a bit long, but it is also because there is a little bit less to talk about with Lewis acid-base chemistry right now until we get a little further into the course when we're going to revisit it in a little bit more of a strong way. So, looking at Lewis acid-base chemistry, we've already kind of touched on it. So Lewis acid base we defined previously as a Lewis base is something that wants to give away electrons, right? And so with that logic in mind, this hydroxide would be a Lewis base, right? Because it's giving away its electrons. Whereas this proton, on the other hand, we would define this more like a Lewis acid, right? Because it is accepting electrons. And these two things combined essentially just have a reaction. And a lot of the Lewis acid-base reactions you can probably think of right now are Bronsted, right? Because it's very obvious that a Bronsted base is going to give away electrons to take a proton, and that proton is always going to be a Lewis acid because it is accepting the electrons from the Bronsted base. So with that being said, there is a true statement that we can make here that all Bronsted acid-base chemistry is Lewis acid-base chemistry, right? It can be defined as both, essentially. However, it's the same idea as the rectangles and squares argument that you may have heard before, where all squares are rectangles, but not all rectangles are squares, right? So it is also true that not all Lewis acid-base chemistry is Bronsted. So what we're going to do during this lecture is we're going to take a look at what Lewis acid-base chemistry really entails because you'll find it is a much broader category than what we've been looking at for these Bronsted reactions. So the first type of category we're going to look at is these Lewis acid-base chemistry associations. All right. So associations are reactions where two things come together to make one. And that's true here for these Lewis acid base associations. So, for example, we could have something like NH3 and BH3, and we could ask, what is the reaction going to look like here? Well, if we think back to one of the first lectures that we actually talked about, we talked a little bit about boron. And the one thing that we said about boron is, you may remember, we said boron is an exception, right? And so we have to kind of think about why boron is an exception. And the reason is because if we take a look at BH3 as is, right, the boron actually doesn't have a lone pair implied because currently the formal charge of boron, remember boron has three, or it wants three valence electrons, right? It has three bonds currently, and if there are no lone pairs, that gives boron a formal charge of zero. So what that tells us is that boron here is missing an octet, right? And because of that, it wants electrons, right? Even though boron is happy being neutral, octets are always good, right? So giving electrons to fulfill an octet is a good idea. And as a matter of fact, nitrogen has a lone pair that it's willing to give. So in this example, we can label our nitrogen as a Lewis base and our boron as a Lewis acid, right? And what's going to happen is our Lewis base is going to come on over. It's going to form a bond by giving those electrons to our Lewis acid. And it's going to form that nitrogen boron bond. And the thing is, once we've formed this bond, you'll notice we're going to have some formal charges changing. Because looking over here, we now have this new bond to boron, which means that boron's formal charge, if we're looking at the formal charge, the good old boron, it has three valence electrons. Now it has four bonds, no lone pairs. So the formal charge of our boron is now -1. Same thing with our nitrogen. Our nitrogen has gained a bond. So it wants five and now has four bonds, zero lone pairs around it. That means the formal charge of our nitrogen is +1. So we actually form this association complex that has charges. And the thing is, this is technically stable due to the filled octet of boron, right? So we can have these association reactions where essentially two things come together to make one, and it's almost always when something is missing an octet, right? So boron is a really good thing to think about when we're looking at an atom that lacks octets. But there's other atoms that actually lack octets, right? So we can take a look at those because it's good to know what these are. That way we can kind of identify when these reactions are going to occur. So, there's a couple atoms that are very common that lack octets, and now there's more than this, but I will say that these are the primary ones you're going to pay attention to. The first is boron, which we've been seeing a lot. The second is aluminum, right? And this shouldn't be a surprise because aluminum is below boron on the periodic table. But then the other one that we see commonly is iron, right? And iron it's in the middle of the transition metals, so it's not one that you commonly see, right? But these are very common things that you're going to see that lack octets. And for the last two, one thing that I'll point out that they have in common, because this is kind of important, is these are metals that are not in the first two columns. Right, because you may remember when we were talking about Bronsted acid-base chemistry, that metals in the first two columns often act as spectator ions. Metals that are not in the first two columns oftentimes act as Lewis acids. All right, so anytime you see these, you should immediately think Lewis acids, right? And it's because all of them lack that octet. So we can give another example of what this actually looks like whenever we are going through and thinking about Lewis acid-base chemistry, right? Let's imagine that we have boron, which is just the diatomic Br2, and it comes in contact with something like this FeBr3, iron tribromide, right? In this case, looking at this set of reactants and looking at the iron, we know that this thing is just like boron, right? It's actually happy and it is missing an octet. And so because of that, that tells us that we're going to use this as a Lewis acid. All right. And so looking at our Lewis base over here, right, that must mean that our Br2 is a Lewis base. The only way that we can use the Lewis base is it has to have some lone pairs for us to use. So in this case, one of these bromines, which does have a lone pair around it, can use one of those lone pairs to attach to the iron, right? And that's going to give us a complex where now the bromine has a new bond connected to it and the iron. And now the iron also has a new bond. And just like we saw up top with the boron, right, we're going to now have two charges where now the bromine has lost some of its electrons by making a bond, so it's positively charged, and the iron has gained electrons, so it's negatively charged. And the same ideas that we were talking about beforehand with conservation of charge are also true in these Lewis reactions, right? So on the left side of the reaction, this side is neutral, right? It has zero charge, and that means that the right side must also be neutral. And as we can see here, it is also zero charge because a positive and a negative equals zero. Okay, so keep these things in mind when we're doing these Lewis reactions, right? We can have these things like iron, aluminum, boron, and other metals that can coordinate and do these associations with these Lewis bases. But these aren't the only things that can do it. We can look at another example of something that's very uncommon, but is a possibility, right? So let's say that we ran into a situation such as this here. So looking at this reaction, we see the right-hand reaction or reactant is a carbon with a positive charge. And as we've seen many times with these, this is missing an octet, right? It's just a carbon that doesn't have all of the electrons it needs. And so if it's missing an octet, that immediately points us to the fact that this is a Lewis acid, right? That also must mean that our alcohol over here is a Lewis base. So you can see that it's not just these metals that can do it, but sometimes other charged species can too. And so with that, this alcohol could come in, give its electrons to that carbon, and it'll form a bond between the oxygen and the carbon. And here's the thing about these, right? When we're looking at these associations, everything keeps the bonds that they came in with, right? So the oxygen was bound to these three carbons that I'm going to label 1, 2, and 3 in orange, right? And so it must still be bound to those carbons, as well as this hydrogen that I have labeled in the orange box in both cases. And what it's doing is it's forming a bond to this other carbon, which is bringing onto it four new carbons, with carbon number 2 being the one connected to the oxygen, which I now have labeled in pink. So one good practice to keep in mind when you're looking at these reactions is to count carbons, right? Make sure that you're drawing in the correct number of carbons whenever you draw the product. Because sometimes you can drop atoms, and if you drop atoms, you're technically showing the wrong product, which means that you've drawn the incorrect reaction. All right. Now, one thing you'll notice that I've been pointing out on a lot of these is these equilibrium arrows, right? Because a lot of these are in equilibrium. But the thing is, we're not going to try and calculate the equilibrium. All right. So don't worry about which side is favored. Right? We're going to get to the point where we can talk about which side is favored later in the course, but for right now, we're just going to leave it as understanding just the basics of this reaction is going to be good enough. All right. So for Lewis acid-base chemistry, at the moment, do not worry about the equilibrium. Okay. So if we have Lewis acid-base associations, that must mean that we also have some Lewis acid-base dissociations. And these are essentially just the opposites of what we were just looking at, right? Rather than starting with two things and moving to one, we're going to start with one thing and move to two. So let's do something like this. So looking at this here, I've already told you it's going to be a dissociation, but we kind of have to understand why something would want to dissociate, right? And looking at this, it's kind of obvious. Because we currently have an oxygen with a positive charge, which is relatively unstable, right? Oxygen is very electronegative. It wants electrons. So essentially, a dissociation reaction is going to give an oxygen some electrons in this case and take them away from something else. And there's a couple things we can take away from. We can either take away from a carbon or a hydrogen, right? And what the hydrogen will become is it would become an H plus, whereas the carbon would become a C plus. If you think about these two in terms of electronegativity, right, the one that would be happier with the positive charge, it's actually the carbon. So, because of this, what's going to happen with the electrons here, right? If we ask ourselves, where do the electrons go? It's to the most electronegative thing by the charge, right? And you're pulling from the least. Oh, sorry, not electron. Whoops, it's supposed to be E neg. You're pulling from the least electronegative thing. So since carbon is less electronegative than hydrogen, and oxygen is the most electronegative thing with the charge, the electrons are going to go from the carbon to the oxygen, and that's going to leave our carbon with one less bond, which means it is now positively charged. And our oxygen gains a new lone pair, right? It had one over here when it was positively charged, now it has two, and it is now neutral, right? So once again, we have a situation where we're not going to worry about the equilibrium, we just need to know this exists. All right? Because even looking at this in terms of thinking about equilibrium, we now have something with a missing octet, which is also unstable, right? And so that's going to happen a lot of times with these Lewis acid-base dissociations. They're usually going to go from one thing to two, and usually one of those two things is going to be relatively unstable, right? Because we can do the same thing with the metals that we were looking at above, right? Looking at this, we could have something such as this here, and I'll tell you that it is a Lewis acid-base dissociation, right? Looking at this, we would say that, well, if this is going to be a dissociation reaction, and looking at our atoms, oxygen is more electronegative than aluminum, right? And chlorine is also more electronegative than aluminum. So the aluminum with the negative charge, it is going to lose electrons and give them to one of these two things. The question is which one? And if we're thinking about electronegativity, oxygen is more electronegative than chlorine. And so what that means is from the bond with the aluminum, the oxygen is going to take the electrons here, right? Because once again, the oxygen being more electronegative than the aluminum means it wants the electrons more, and it's more electronegative than the chlorine, so it wants the electrons more than those two. So now the oxygen is going to bear the negative charge because keep in mind it had two lone pairs here, and it ends up with three. And then we now have the aluminum that is missing an octet. So this is another example of a Lewis acid-base dissociation reaction. Now, one good thing that you can keep in mind about all of these reactions is on the exams and quizzes, I will state if something is Lewis acid-base chemistry, right? So you don't necessarily need to immediately be aware of these reactions being Lewis acid base. At the moment, I will tell you that they are Lewis acid base. But keep in mind, as we go throughout the course, we're going to see more Lewis acid base chemistry, and it's going to start to become more apparent, and I'm going to stop telling you when something is Lewis acid base. But at least for exam one, right? So this is exam one specific. I will tell you when something is a Lewis acid-base chemistry reaction. And the two types that you really need to worry about right now are the associations, where it is two things coming together to make one thing, normally because something has a missing octet, and Lewis acid-base dissociations, where one thing breaks into two, and it usually leaves you with something that is missing an octet. Now, that being said, there is an important aspect of Lewis acid base that the book really touches on that I also want to get to. And so it is the entire basis of organic chemistry, right? Because we've been dipping our toes a little bit into organic chemistry, but in reality, organic chemistry is all about Lewis acid-base chemistry, as well as, I guess, Bronsted, but of course that falls under the umbrella of Lewis acid-base chemistry. And the one thing that is true about all of organic that you guys have probably noticed so far is that positive charges love negative charges, right? This is just a physical thing that everyone is probably aware of. It's the same thing with magnets, right? The negative and the positive end are attracted to one another. And so that's true with these, I guess, reactions as well. Positive and negative charges love each other. And we've actually come up with a name for this idea in organic chemistry, and that is the idea of nucleophiles and electrophiles. And so nucleophiles are just a fancy name for Lewis bases, right? Whereas electrophiles are a fancy name for Lewis acids. And the whole idea behind these is that nucleophiles are these negatively charged things that like giving away electrons. On the opposite side of things, electrophiles are usually these positively charged things that like accepting electrons. And so what we're going to start doing now, which will actually help us a little bit later, is we're going to change the vocabulary a little bit when we look at Lewis acids and bases and start to define them as nucleophiles and electrophiles. Because what this boils down to is what I'll call the golden rule of organic chemistry, right? And it's very, very simple. It is that a nucleophile will always attack an electrophile. It will always give its electrons to an electrophile. And if you take one thing away from the class, that golden rule should be it. Because understanding that will get you through most of the rest of this course. Okay, so let's look at another Lewis acid-base reaction, another couple, and we're going to start defining things as nucleophiles and electrophiles. So let's go into another example. All right. So for this here, in this reaction, we see that, hey, look, it's iron, right? And as we talked about previously with iron, it is a Lewis acid, which means, based on our new definition, it is an electrophile. All right. And one of the things that we do know about electrophiles is we stated something right up there where we said they were positively charged, right? And this iron is positively charged. But the thing is, it is partially positively charged, right? And we know this because all of these bromines are pulling dipoles, right? These bromines are all partial negatives because they are more electronegative than iron, but that does leave the iron with this nice big partial positive charge, and it's an electrophile. On the other hand, if we look over here, we have our sulfur that has a lone pair, and we know based on what we've been talking about today that this is a Lewis base. But that also means that it is a nucleophile based on definition. And nucleophiles have partial negative charges or full negative charges. And in this case, the sulfur is no different, right? It's pulling a dipole on this carbon down here, which means that the sulfur is partial negative. Now keep in mind that means that the carbon is also partially positive, but it is not as positive as the iron, meaning we don't care about it, right? So from here, what we can do is we can say, all right, if the nucleophile gives electrons to the electrophile, it's going to form a bond, right? And we're going to end up with a iron that has a negative charge, a sulfur that has a positive charge, because remember, it still has the bond to the hydrogen and the bond to the other carbon there. And that's going to be our product, right? So a nucleophile and an electrophile came together to make one thing, right? If we take a look at now a dissociation, we can imagine that a dissociation is essentially going to give us something very similar, but this time there isn't necessarily a nucleophile and an electrophile to play with, right? This is a different type of reaction because remember when we're looking at these dissociations, they make the Lewis acids and bases. They do not start as a Lewis acid or base. So looking at this one here, the bromine is positively charged. It wants electrons. The iron is negatively charged. It has too many. And the bromine is also electronegative, so it's going to pull the electrons towards it from that bond. It's going to break that bond, and it's going to dissociate to make the Br2 and the FeBr3. And now if we look on the right side here, we can identify that the FeBr3 is an electrophile, right? Because this is the same as we saw up there, where the iron is missing that octet. It wants electrons, which means that the bromine must be our nucleophile, right? Because it has the electrons to give. So dissociations make nucleophiles and electrophiles. All right. And so essentially, whenever we're discussing Lewis acid base chemistry, it is all going to be within the context of nucleophiles and electrophiles from now on. Okay? And the thing is, this would be very simple if this was the only piece of the picture. All right, but this is not all that has to do with nucleophiles and electrophiles because we're going to start looking at more of the big picture ideas, which is going to be combining reactivities. And I will say that for this, you'll want to know and understand this a little bit, but I will guide you on it as we get to the exam. All right? Because going into this is going to be more of a deeper thing that we talk about later. But at the moment, you just have to know that it exists. Okay? So, what if we had a situation such as this one here? All right. If I were to hand everyone this reaction, right? Just not even thinking about it in the context of this lecture. The first thing that I would hope you'd do is you would look at H3O plus and you would say to yourself, this is, as we've defined it in the past, a strong acid, right? It is really good at protonating things for Bronsted acid-base chemistry. And so what that would mean for us is if that's a strong acid, this right here is going to be a good base, right? And so this first thing that we're seeing here that's about to happen is this is an example of a Bronsted acid-base reaction, right? Where our base is going to come on over, grab a proton, give electrons back to whatever atom it's attached to, in this case, the oxygen, and it's going to generate a set of products, right? And we hopefully at this point kind of understand this process, right? It's an equilibrium where we should be able to determine which way it's pointing. But the thing is, now that we've gotten here, there's something else going on, right? Because of the knowledge that we've learned during this lecture. And that is, you'll notice that this product that we've generated, the conjugate acid, now has an interesting resonance form, right? It is this positive charge here on the carbon. And this isn't necessarily the major resonance contributor. But what you'll notice is that this carbon is missing an octet. And since it has that positive charge and it's missing an octet, that is the primary example of an electrophile, aka a Lewis acid. And funny enough, we've generated water, right? And this water is a nucleophile, right? Because that oxygen is partially negatively charged. So if nucleophile gives its electrons to electrophile, we have suddenly generated something a little different. This is now another product that we could form. So big picture, as we go along, is that these reactions are going to start being used to generate other things in sequence, right? And the reason that I've been harping a lot on acid-base chemistry being so important is because it's the backbone of a lot of the things that we're going to do later on that's going to lead to these secondary Lewis acid-base chemistry reactions, right? Now, that being said, on the exam, I'll give you forewarning that I am just going to primarily ask you for a single step, right? I will say predict the products of this reaction right here. I will not go ahead and ask you if anything further happens. Now, that being said, there is the possibility, and I will likely do it with a reaction incredibly similar to this, that I will tell you that two reactions happen back to back, and I will say that the first one's Bronsted, the second one is Lewis, and to determine the products of those reactions. Now, if I ask that, this is fair game. Okay? So, with that being said, that is everything that I have to talk about for Lewis acid-base chemistry today. Hopefully, it made a little bit of sense. But of course, it's going to be very well stated on your exam when it's occurring. So don't worry too much about knowing when the reaction is going to occur. Just know how the reaction is going to occur. Next time, we're going to hop into something a little different before we get to the exam. And I promise you that this is going to be the hardest content that we see before the exam. That way, everything calms down a little bit as we go into the final week here before exam one. See you next time.